Now we do a more complicated problem. In this circuit, we use a voltmeter to measure the voltage of an inductor powered by a DC voltage source. The measurement range of the voltmeter is 50 volts. The internal resistance of a voltmeter is 10K. We know that at time 0 the switch is opened. We want to find out after the switching the voltage on the voltmeter. This idea looks weird, but has realistic meaning. We want to make sure that after switching, the voltage on the voltmeter will not exceed its measurement range, so as to keep it safe. Let's calculate. Based on the habits gotten from the previous simple problem, we need to draw the circuit before switching, which is a resistive circuit. Inductors are short circuit for DC, which has been discussed previously. So we can find out that IL0 negative is equal to 10/10, which is 1 ampere. Next, we need to draw the equivalent circuit at time 0 positive. Here, a current source with 1 ampere substitutes the inductor. For such a circuit, it's obvious that UV is equal to -1 times 10K, which is equal to 10K volts. This is just a number which means nothing to you. But by comparing the measurement range of the voltmeter, which is 50 volts, we can see that after open, the voltmeter will be broken. Please consider why. It is related with a specific characteristic of inductors. Because of the magnetic flux linkage conservation for inductors, the energy stored in inductors need a loop. If we open the power supply branch, there will be a high voltage on inductors. If the inductor is connected with a voltmeter, the high voltage is on the voltmeter. If there is nothing connected with the inductor, from circuit theory, there will be a voltage with infinite value. Now let's see a simulation. This is the simulation for the circuit. Please check the voltage source value, voltmeter value, inductor value, and the resistor value. They are exactly the same as the circuit. The channel A of the scope is connected to the one side of the voltmeter. The other side is on the ground of the circuit, which is the other side of the voltmeter. Maybe you are not familiar with such an element. It's a key-controlled switch. That means if we press the space key, the state of the switch will be changed. Now let's see. What will happen if we press a space key in the circuit? The current state is that the source is powering the inductor. After we press a space key, the switch is opened. The inductor is powering the voltmeter. Now we run the circuit. Turn on the switch. Stop. We trace back the waveform and use a cursor to have a check. Please see that at this time, the voltage on channel 1 is -9 some K, which basically coincides with what we got from analysis. We just analyzed and simulated such a circuit. Is it a good one or bad one? I'll tell you that it might be a good one or a bad one. Why? From the good perspective, we can use this property of the inductor to design an ignition device for cars. In between here is a small air gap. The switch is opened at 0 because there will be high voltage on the inductor. The air in the gap will be broken and thus generate a spark, so the car can be ignited. That is the benefit we got from the non-open property of the inductors. But we do need to measure the voltage on the inductor. What can we do under this condition? engineers have provided the solution. The switch is open at 0. We add a diode here. Because the voltage is upper positive and lower negative, the diode is off. So the voltmeter is measuring the voltage of the coil. That is to say that this diode has no effects on the measurement. But after the switch is open, we can find that this is a loop for the current of the inductor to flow. So the voltage of the voltmeter is 0. Thus we protect the voltmeter. Here we need to emphasize that for any electrical phenomenon, we can either utilize it or prevent it. That is the charm of the circuits.